limit stuff visually and algebraically and all that, but really just quickly in summary, when we started this, we showed limits visually. So limits, looking at a graph. Hopefully by now the concept has sunken in, and if you see the graph in front of you, you got it, hopefully. Limits on piecewise functions. So again, if you're looking at the piecewise function, great. Should be easy. If you're looking at the equation of the piecewise function, making sure that you're looking at the limit as you approach whatever number it is from the right. So plug the number in when you're coming at it from the right, and also the limit as you approach the number from the left, and your overall limit is only going to exist if these equal each other, right? So oftentimes with the piecewise functions, if the pieces get cut off at x equals 3, so before x equals 3, they're using one equation, and after x equals 3, they're using another equation. You want to plug 3 into both of those to see if coming from the left and coming from the right, it's the same thing. And then we did like limits by direct evaluation. Direct eval. So that's where you would just plug the number in. If you're looking for the limit as x approaches a number, you literally just plug the number in. The issues come up when you don't get an answer, right? If you get 0 over 0, which happened a lot, you have to then look to manipulate. And manipulating can include anything like factoring and cancel, rationalizing a numerator, what else do we, clearing complex fractions. There's, when direct evaluation gives you that indeterminate case of 0 over 0, there's the ways that we manipulated to kind of work those kinks out, and then once we got things to cancel, we would replug in the number, and then if we got an answer, we got an answer. Okay? Then there's cases where you plug in and you get a number divided by 0. As long as that number is not 0 over 0, this limit does not exist. But then the further stipulations come in when you get that it doesn't exist, but it's not existing because there's a vertical asymptote there. And if there is a vertical asymptote there, then you need to further delve into, is it going towards positive infinity as I approach that asymptote, or negative infinity? And are we coming from the left, or are we coming from the right, kind of thing? Okay, so if you're looking for the limit as you approach a number, either your exact answer will come up, or you'll get an indeterminate that needs some finagling, or you'll get a does not exist that also needs some further exploration and thought regarding, is it a vertical asymptote or not? Okay? Sometimes you would get the number divided by 0 and does not exist because the graph doesn't exist there, right? Like if you think about a radical function, if you were asked for the limit when x is negative, as x is approaching negative 5, if you plugged in negative 5, you'd get that it doesn't exist, probably because you're trying to take the square root of a negative, right? There's a reason, there's a difference there. This one doesn't exist because the graph doesn't exist, so your final answer just sticks with does not exist. Versus if you're approaching an asymptote, that's not existing because of the asymptote, and we get more specific, okay? And then the last thing we just did, and we're going to continue to do today, is our end behavior limits. What are our limits as x approaches either positive infinity or negative infinity? And that's end behavior, horizontal asymptote stuff. Okay, so that's kind of the summary of what we've done with limits so far. Like I said, we're going to continue on the notes today. As long as you guys had no other homework questions, we'll just continue on our notes from yesterday. I'm not going to collect your homework because the rest of that sheet is going to be it for today. Okie doke. So take out your notes from yesterday, the note sheet that you picked up on the way in, ignore it. Okay? So on the back of yesterday's note sheet. Yesterday we did all rational equations. So all the examples from the front were rational. If you look at the back of this, we have a log graph. We have a rational sort of, but mixed with a radical type function. We start to get into these crazy functions, exponential, a rational, but mixed with a log. That's interesting. These are kind of your special cases where the horizontal asymptote idea is not going to work because it's not a straightforward rational function. Okay? So we're going to have to tap into what we know about these graphs, maybe taking a little more time to sketch these graphs out and so on. So, in general, like a log graph, this one's not so bad because at least it's a somewhat reasonable equation, family of functions that we've done before. But a log parent graph does this. And you have to know these pretty fluently so that you don't bury yourself in confusion when you get to a problem that can't be done with horizontal asymptotes. That's the parent graph. What transformations occur to that parent graph here? Olivia? Okay, that comes second. What comes first? Right 3 units. There's your horizontal shift, right 3 units, and then a vertical reflection. So this intercept, which is at 1, is going to move over 3 units, 2, 3, 4. It's going to be there now. So, briefly, the graph would look something like that. But then it's getting flipped vertically. So this is what the graph would look like. This one here. If I do it more boldface. Now, on the parent function, did we have any asymptotes? Do you have any asymptotes on the log parent function? If so, where are they? Mitch. At 0. Anything else? There's actually not a horizontal one. This, although it flattens out and it doesn't increase as quickly, it still is going to increase indefinitely. So it does look like you want a horizontal asymptote because it looks like it's flattening out. Log graphs actually don't. Okay, they do keep increasing. So when we shift that vertical asymptote right 3, and when we, let's put it there, my scale's a little off, and when we flip that vertical asymptote right 3, it's just over here. So when you look at this question, okay, so just like this didn't flatten out up here, this is not really flattening out. This is going to continue to decrease forever. Okie doke? So what visually now is our limit as we approach infinity? Marissa. As we approach infinity, the graph is going towards negative infinity, correct? And what is the limit of this graph as x approaches negative infinity, would you say? John? This graph right here, are you looking at? Where's 3 coming from? The asymptote? But that's an x value. That asymptote is an x value of 3. Anytime you're asked for the limit of a function, you're asked for the y value that it's approaching as x gets further and further closer to a specific number, or in this case, as x coordinates approach negative infinity, what are the y coordinates approaching? He says infinity. Who's got another guess? Because that's incorrect. I'll explain why in a second, but as x approaches negative infinity, what's happening to our y values? For example, because no one is raising their hand with a guess. Okay, why are you saying it doesn't exist? Right, your x's can't go towards negative infinity. I mean, they can, but if you plug in an x coordinate of negative 1,000,000, there's not a y coordinate paired with that. If you plug in an x coordinate of negative 100, there's not a y coordinate paired with that. If you plug in an x coordinate of 0, there's not a y coordinate paired with that. So as x approaches negative infinity, because the graph doesn't exist over here in the negative infinity direction, neither will the limit. So that does not exist. Okie doke. All right, next one. This is a new beast because there's no like parent graph for this. So the first thing I immediately think about here is it's not exactly a rational function, but when you take the cubed root of something, that is the same as raising it to the what power? 1/3 power. Very good. And even though like we're not going to raise the binomial to the 1/3 power, we can at least wrap our head around what the leading term of it would be. Because 3x squared to the 1/3 power would be the cubed root of 3 as a coefficient, and then x squared to the 1/3 power. When you raise an exponent to an exponent, what are you supposed to do? What's the rule? Multiply. 2 times 1/3 is x to the 2/3, ... There would be the rest of an ugly looking polynomial. But when we're thinking about our degree rules, we only really care about the leading term anyway. So our leading term has some crazy weird coefficient, but the exponent is 2/3, so the degree is 2/3. And what's the degree of our denominator? What is the exponent on this x? 1. So if you were analyzing this, 2/3 versus 1, is that small over big, big over small, or same over same? Small over big. 2/3 is smaller than 1. And small over big has a horizontal asymptote where? Y equals 0. So to the best of my knowledge, that's what the horizontal asymptote would still be, even though we kind of had a crazy degree rule situation going on there. Okay? The other thing, just for the sake of checking it, is are there any domain elements that we'd have to consider being not feasible? Is there any x value that we couldn't square and then multiply by 3 and then subtract 2 and then take the cubed root of? Or are there any x values that wouldn't be feasible for 5x plus 1? Yep. Negative 1/5 would certainly be an asymptote, right? And we would care about that if we were asked for the limit as we approach negative 1/5. So good to know, but it doesn't really affect us here because we're not being asked about the behavior surrounding negative 1/5. We're asked for n behavior. So I'm really kind of getting at the same idea here. Are either one of these not going to exist because like the function doesn't exist over there? And this will exist pretty much everywhere except for at negative 1/5. So we do have n behavior going in both directions. And because we have a horizontal asymptote, that's it. 0 on both ends. I'm going to plug this in. So we have numerator 3x squared minus 2 to the 1/3 power boy. Divided by 5x plus 1. And I'm going to start with a zoom 6. I have no idea what this graph is going to look like. Okay, so it's actually a pretty traditional rational graph. You can see there's definitely a vertical asymptote really close in there. That's the negative 1/5, I'm going to assume. And then it looks like it's above the x-axis a little bit and then evens out. Probably negative 10 to 10 is actually too big of a window. We might see it a little more clearly if we do negative 2 to 2 and negative 2 to 2. It'll just give us a better feel. Okay, so there was a weird little kink that traditional rational graphs don't have. Same with this one right here. But we don't necessarily have to worry about that because, again, we were concerned with end behavior. So it goes up above the x-axis. Now, because I'm too close, I'm kind of losing what happens as I go towards end behavior. So maybe I change my x window from like negative 2 to 2 to negative, I don't know, let's go back to negative 10 to 10, at least on that one, so we can see out a little bit further. So you can see it shoot below the x-axis, but then you can all agree it's getting closer and closer to y equals 0. And it shoots above the x-axis, but again, you can see it getting closer and closer to the x-axis. Okie doke? So we don't really ever need to know how to graph that full function. There's just key features we do want to know about. The vertical asymptote at negative 1/5 and the horizontal asymptote. Okay? It's got the properties of a rational function in a lot of ways, but it had a couple extra kinks in there. Okay? All right, exponential functions. E to the x as a parent graph looks like that. Right? Anything to the x power looks like that as a parent graph. So, Nate, what does the 3 do? As far as the transformation is concerned. Horizontal or vertical? If the parent graph is e to the x, is that 3 happening inside the function or outside the parent function? Isn't the 3 slipped in literally inside the function? Okay, so that's inside. So is that horizontal or vertical? Horizontal. Anything inside is horizontal. Now it's multiplying by 3. So is that a dilation, shift, or reflection? Good. And specifically a stretch or compression when it's horizontal and the multiplier is 3. Compression because everything horizontal happens backwards. So that's going to compress the graph inwards by 3. Does that affect your end behavior at all? No. So I really don't care about that. Okay? Now, the next thing is the negative out in front, which, Bridget, is what? Horizontal or vertical? Vertical. So this is going to flip vertically over the x-axis. Does that affect end behavior? Yes. Not so much on this end, but definitely on that end. Agreed? And then everything shifts up 1. Does that affect end behavior? I think so. Not on this end, because this is approaching negative infinity. What is this currently approaching before I shift it up 1? 0. But if I shift it up 1, that horizontal asymptote that was there is also shifting up 1. So it doesn't affect the end behavior going towards the positive infinity direction, because as this function approaches infinity, your y values are approaching negative infinity. But as this function moves to the left now, because of that shift up 1, the y values are getting closer and closer to the horizontal asymptote of 1. Horizontal asymptote got moved up because of that shift up 1. Does that make sense? Okay, any questions on that? All right. Oh, I don't like the look of this. Not one bit. Natural log of x divided by x to the third plus 3. Honestly, I can't even begin to imagine what this graph looks like because I can't even argue that this is a rational graph. A rational crossed with a log, I don't know. I don't like it. But what I can do when all else fails is I can plug in a somewhat big number or a series of numbers and see what happens. Like let's say I plug in 10. I'll plug in, as I approach infinity, I'm going to plug in 10 and see what I think of it. And I'm going to plug in 100 and see where that's progressing. So if I plug in 10, what's happening when I plug in the natural log of 10? Think about the natural log graph. Looks like this. It's always increasing, right? But not very fast. Okay? Natural log of 10 versus natural log of 100. Right? Natural log of 10 would be like here. Natural log of 100 is way, way, way far away. It's going to be bigger, but not by much, because that's kind of the behavior of your log graphs. So even though log of 10 and log of 100 is a bigger number down here, not by much, right? So this is growing pretty slowly. 10 cubed versus 100 cubed, though, that's a huge difference. So that's like skyrocketing. So your numerator staying fairly consistent, growing but fairly consistent. Your denominator is shooting up. So as you get towards 100, the gap between these is growing significantly, right? With the smaller number on the top and the bigger number on the bottom. As the denominator gets bigger and bigger and bigger, like if you had 5 over 1,000 versus 6 over 10 million, which one's smaller? 6 over 10 million, right? The number is getting smaller due to the way these are growing. And it's getting smaller and smaller and smaller, approaching, when that happens, 0. Okay? If I plugged in the ln of 1,000 over 1,000 cubed, this portion would be approaching 0 as that gap increases. Do we follow that? Okay? And so if that portion's approaching 0, and you add 3 onto that, what's 0 plus 3? 3. That's your limit. The negative infinity is going to be easier, because if you plug in negative 100, what immediately happens when you try to take the log of a negative number? It doesn't exist. That graph doesn't exist in that direction. Therefore, the limit doesn't exist in that direction. Okay? So features to think about. A sine graph, very quickly, as you approach infinity or negative infinity, this just keeps oscillating back and forth. It's not narrowing in on any value in either direction. It's not getting closer and closer to anything. Therefore, these trig limits don't exist. They have no end behavior because there is no end of the graph. It just keeps bouncing back and forth. Okie doke. 9 is going to be a little bit different. Let me ask you this. As x approaches infinity, like if I were to plug in sine of 1 over a million, what happens to 1 over a million? That's getting closer and closer to what? 0. And if that's getting closer and closer to 0, what is the sine of 0? You should know this. The sine of 0 is 0. So it's almost about exploring what the inner part of it is is approaching, and then what would the sign of that number be? Same thing here. Sine of 1 over negative a million is kind of like the sine over 0. It's coming from the negative side of it, but it's still like the sine of 0, which is also approaching 0. Okay? A lot more to think about with these odd functions. So your homework for tonight is the remaining part of that worksheet, and we'll move your quiz to Friday.